¿Aquí? Sí.
I'd like to thank David and the whole WeightWatch consortium for inviting me to introduce the technological solutions we propose at our research group, CERTEC, from the Polytechnic University of Catalonia, in order to increase safety in interface fires, but especially at a microscale level. I'd like to preface my conference by highlighting the main points discussed during the morning, and I would like to stress the legal framework, and I would like to point out its shortcomings. And then I will introduce this term, performance-based design, which is an important methodology from a close scientific community with which we've been working for a while, and I will introduce a couple of examples. You will see it is an extract of a full project, but I think that with these simplifications you will be able to see the potential we have at our hand. And then we will finish with some final remarks in order to open the debate at the round table. As you can see, I buy the trans-scale approach explained by David in all these conferences and the framework of this project, and I totally agree that the interface problem sees the interaction of different issues at different levels. So solutions require to provide a context to each problem and to react accordingly. We've spoken about prevention at microscale, prevention strategies at microscale, but in this conference we will speak about microscale, which could be the preventive options or methodologies that could be implemented in order to define our actions, so that at the end of the day we increase safety to protect goods, but also to increase people's safety. Which are the essential points so that the microscale is so vulnerable? I think is the interaction, the complex interaction of three main agents: fuel, building elements, which are vulnerable, and then people, the existence of people. So we will try to summarize what we've seen this morning. Then we have fuel at the microscale. It doesn't need to be just vegetal fuel. It can be hedges, as we see, obviously. But then we also have elements which do not belong to the vegetation and could cause great problems at microscale. Then we have fuel around this household, and this could interact with our building elements. Luis Mario explained it before. The Mediterranean reality doesn't see constructive or building realities which are very vulnerable, because we tend to use materials with little reaction to fire. But even so, we can identify a list of vulnerable elements, for example, openings or pavings, terraces, so on and so forth. So what do they all have in common? They are either flammable, they burn when there is a flame, or if they are not, they are sensible to fire, because they could crack and lose mechanical properties, for example. This is a side of building elements associated vulnerability, but then we have another trait. Some elements cause an intensification of heat transfer phenomena. And I'm talking about two clear examples. First, the deposit of a firebrand with an angled section. If this falls on a flammable material and this is confined in a corner, there would be re-radiation mechanisms that would boost the ignition process, creating this firebrand. But then we have more. If there are geometrical characteristics in the households with certain openings, there could be local turbulences creating a flame dragging towards these structures, and all these aspects contribute to more vulnerability in our houses. And then we have the presence of people, residents and responders. We've mentioned today that in certain areas we are trying to promote a more active confinement. So the presence of these people and their safety makes us see that this interaction between fuel, residential fuel, and building elements is an interaction we should try with immediate character, because this is a microscale scenario. Here we can see different ignition mechanisms which interact with each other. We've spoken about firebrands, exposition to heat flow, and then flame contact. All these elements could come from the main perimeter or from flammable objects close to the houses and which have ignited due to an appropriate fire spread. Firebrands, we all know, is the convective transport of material with spotting fire or with flaming fire. It could come from the from the main perimeter or from other perimeters, and it can lay on flammable materials and ignite them. And then exposition. It can come from flames from the main fire or from flames arising from close objects. This heat flow is radiant flow, which can ignite flammable material, but then it can also damage sensitive areas that could lose their mechanical properties. And lastly, we have flame contact. In an intermix situation, we would have the flame input, so to say, from the main fire, from a microscale and a residential development, and then we would have flames from the residential fuel, and this creates heat due to radiation and convection. So this contact creates the situation with the most heat contribution, and this will be the worst case scenario. Our dear colleagues from CSIRO in Australia, Blanchi and Leonard, have done an extensive field work trying to trace the interface fires in the last 40 years, I would dare to say, in Australia. As you know, they had huge problems with interface areas. They've traced the Canberra 2003 fires, the Victoria 2009 fire, and they reached the following conclusion. The probability of losing a house is in their territory mainly linked to the interaction of 1. Firebrands, flammable material, resulting in flames, and all in all, it's too close to the houses. So we could say that ignition at microscale is a combination of these 3 agents. What our Australian colleagues have seen is also applicable in Valencia. We could say air attack would result in firebrands falling in these residential areas. This residential fuel ignites, and these flames are too close to prevent the destruction of a household. Regarding the legal framework, this is something we've mentioned this morning. I guess we all agree on the fact that operations at mesoscale are to a certain degree already regulated. What do I mean? For example, in Catalonia, we have the 2003 law with a decree 123, and then the law 2014 arising from the Ampurdà fires, and these are the regulations that we have in place, establishing that we need a 25 perimeter, then we need dry fuel, and so on and so forth. These laws have been taken a step further in France, establishing certain distances, such as a 50-meter distance. Raúl mentioned before, why 25 meters? What do we do with 25 meters? Well, these are based on scientific evidence, on firefighting experience, but above all, on calculations which are, to my understanding, too simplistic. Currently, we face a complex reality, so we cannot trust these calculations. Another researcher is Brett Butler from the USDA Forest Service from Montana, and he has worked on security distance for firefighters. He held a webinar in 2014, an open webinar. The title was something like Calculating Safety Zones, something similar. It lasts for an hour and a half. And here, you all risk your lives fighting fire. And if you haven't watched this webinar, I really recommend it. It explains the history of calculations for safety distances. And he's been working on this issue for many years. And here, he says something like recommendations regarding safety distances at the interfaces or safe areas. These methodologies used to do so were done under the following hypothesis: a plain area without wind and considering only radiation heat transfer. So this is my first wake-up call. We could debate about this and reflect on this, whether it is worth it to reconsider these calculations and to go a step further so we can deal with the current reality, which is much more complex than this. So we have this warning from Mr. Butler, and it should inspire us to reflect, to see what can we do in our local territory. Regarding microscale, if we speak about the legal framework and building of houses, as far as I know, there are 2 examples. Maybe there are more, but to my understanding, there are just 2 examples of 2 countries where in their technical codes they add some kind of standard in order to classify and regulate how buildings should be done in interface areas. First, we have the 3959 Australian standard complementing the Australia Building Code, and the second one is the Californian standard. These standards establish, for example, the Australian standard, as you can see in this screenshot, establishes that, to start with, it classifies interface risk areas through simple models of heat transfer by pigeonholing the flame radiant power coming from a main front. So we are neglecting here anything related to residential fuels, which are mainly responsible for houses burning. Secondly, it classifies the risk based on these models by simulating the flame, and on this basis they provide recommendations depending on the risk category. And they provide recommendations of materials to be used, configurations, structures, and so on and so forth. Okay, these are just examples which we could debate about whether they are needed in our country to go a step further. And regarding the fire prevention code, maybe we could integrate some kind of building standard. I remember that back in 2014, a student of Master Fuego, Claudia Gallardo, had a final master's work, and he proposed a first draft for a complementary technical instruction in order to complement this building code in interface fires. So he based this work on a very basic heat transfer model, but this was the first draft, and he did so because Claudia was working with the local fire prevention service in Catalonia, and we went through his work, and I contributed with my own ideas in order to test the scientific validity, and we suggested that he could start a PhD, but he was trying to get a new job, and well, this process didn't conclude, but the draft was there. It was just a master's final work, and this was an interesting starting point in order to regulate these buildings in interface areas. So I would like to propose a new discussion item, a new wake-up call, to see that we have examples in situations and places where people implemented standards which are good examples. Obviously they can be improved. Some are based on very simple examples, but this is a starting point, and these offer general solutions to a very unique issue, and where there is a huge margin of freedom. There are no two plots are identical. So we could try and think which solutions we can bring to the table, but I'm just opening this debate. Okay, after this brief introduction about our key points with the interface situation, I would like to speak now about new methodologies, because I think we need to go a step further. We need to meet the safety needs for people, residents, goods, and we would like to propose a new methodology that would be helpful. We could analyze unique risk situations and to test the validity of the current recommendations, and obviously we could infer new recommendations to establish codes and specific standards. I am speaking about the performance-based design, CFD. And what is performance-based design? We've borrowed this term from a very close technological scientific community, and this is the fire engineering scientific community, and I think we should interact with them. We could create new synergies. It's a very interesting community, and as Raúl and David put it, it's a two-branched emergency, what we are facing. And if we work together and we look for common points between the fire engineering community and the firefighting community, we could create synergies, which could be very interesting. So, performance-based design is a very common practice in countries such as Canada, Australia, or the US, New Zealand, Singapore. And currently, in this community, something is arising. This is arising in countries, Mediterranean countries such as Spain, Italy. So, it is a new aspect gaining important momentum. So this is based on the fact that there are many unique designs, special designs with a high degree of uniqueness and prescriptive norms establishing that we should meet a certain code. Well, these norms are not sufficient in these cases to ensure safety. We're talking about designs with new materials being developed currently. We are talking about structures such as atriums, train stations, airports. So these are buildings, premises that are not covered by the general code in case of a fire. So this is the idea of performance-based design in fire engineering in urban areas. And then this is the PBD, which is the acronym for performance-based design, is based on applying scientific knowledge and principles of engineering in the design of measures which are needed to protect people and their environment, and it is based on safety goals regarding fire. Well, this is actually a bit more complex than this slide, but to explain it, we could say that this methodology has three main steps. First, defining objectives and performance we would like to achieve. Objectives: protecting people, protecting property, and facilitating firefighting operations. So, with these objectives, we need to decide what is the performance we would like to achieve regarding design. Once this performance has been defined, we need to define the types of fires that could happen in our system, and therefore we need to identify which fuels could come into play and which environmental factors would be. And then we should evaluate quantitatively to see if we are achieving these goals. These simulations need to be carried out with powerful tools, and these are the CFD tools. These are computational fluid dynamics tools, and they solve the transfer of matter in three dimensions, and on each cell we could see how energy is being transported, so flow and energy. So there are CFD tools specific to fires which allow us to evaluate the exposition to heat and flame contact, and in our case we have houses and people. But furthermore, they contribute to a better understanding of physical phenomena happening in a fire. An important aspect I would like to highlight here is that most CFD tools, in most of them, fire is predetermined, is not foreseen, is predetermined. If we know the heat power and the combustion speed, we could determine the shape and behavior of this heat and its flame. So in these tools, we can also set up the building, the house configuration through CAD tools. So we include, for example, thermal characteristics and properties through CAD tools. So if we are able to determine properly the fire, to specify the building characteristics, and if we have the computer resources, sufficient computer resources, because obviously we cannot use just any laptop, we need very powerful machines. If we have these 3 points covered and a realistic fire, building characteristics defined up to a very high detail, we would have very realistic results. Therefore, we've spoken about the methodology with some of you, with David, we've spoken about opportunities arising from this methodology, and I do believe that we could inspire ourselves in this performance-based design in order to analyze global scenarios or small details of this microscale we would like to analyze further, and how establishing performance, defining scenarios, analyzing the result of fire, and analyzing temperature, speeds, heat flow, smoke exposure, and so on and so forth. But on top of that, I think it will help us to acquire new knowledge on fire dynamics, because these tools explain what is happening in this fire and why it behaves the way it does. So with these tools we can learn what's the effect of the re-radiation and then intensification of heat transfer. David has shown this picture, and you've spoken about these methodologies, and we can see local turbulences, and then there is fire dragging phenomena under these little roofs, and CFD tools allow us to observe these phenomena and to learn from them. And I think the forensic analysis allows us to state or rebate some hypotheses. So I will try to give you a couple of examples of that we've worked with. These are simulations, and this is an extract of a performance-based design. And I think that with this extract you will get again a general idea. And also you will be able to extrapolate the forest from the tree, so to say. So let's say we use this to study the performance, the characteristic of a window which is exposed to fire. It's a double glazed window, and we have a air channel. And here we have a Persian blind, a PVC Persian blind, which would be our goals here. Well, we would like to ensure that these warranties the integrity of the system, or we would like to ensure the living conditions inside the house. To do so, which are our objectives and which is our efficiency level? First, we could say that the window shouldn't go beyond the crack point, which is 150 degrees, or that the PVC Persian blind shouldn't get to the deformation point, 140 degrees, and that the temperature inside of the house should be under 60 degrees, which is needed for survival. These threshold figures cannot be arbitrary. We need to be based on scientific publications scientific data, experiments, scientific tests, such as the one mentioned by Luis Mario in the framework of the WeWatch project. So we need to set these levels, and then we define several scenarios. One would be the flame impact on a tree, a Douglas fir, at 30 centimeters of the facade. And why? And now you would ask yourselves, why Douglas fir if you are interested in hedges? Why do you take a different kind of tree? As I was telling you, for these simulations we need data for combustion levels. And Rudimel, he worked in mist and now is working at the Forest Service in the US. He carried out a research and he burned a great deal of Douglas fir trees and analyzed the results. And he monitored these experiments. And now we are using their data, which have been very useful to simulate this scenario. So I would like to launch the message that, okay, if you are concerned about certain species and elements and would like to use this methodology, we need to propose a experimental program so that we have scientific-based data. If there is no option to do so, then we could gather information from real fires. We could trace realistic curves for other burning species if we have an Arizonica hedge, and if we can observe how it is burning, what is its flame geometry, how long it lasts. If we can estimate the fuel load before and after, then maybe we could establish a more or less realistic curve as the one here. Ideally, in an ideal world, we would carry out tests and experiments, but if we can't do so, previous experiences can be helpful. So in this first scenario, we say the ambient temperature is 20 degrees, and we say there is a perpendicular wind to the facade to make sure that the flame would hit the facade. Simulation of the fire is here. We see the net heat flux here. The scale is very small, but obviously red is around 45 kilowatts per square meter. So values are really high. We have a Douglas fir burning at 30 centimeters. So these values are extremely high. In these simulations, we can introduce virtual sensors to obtain information about temperature, pressure, heat fluxes, and here we can see that regarding the external glass temperature, this close flame is getting to the crack point threshold levels, and the PVC is beyond the threshold level. But regarding the inner side of the glass, the increase is not important. So we can conclude that objectives 1 and 2 were not met, but objective number 3 was met, and therefore this system does not meet the requirements. This is just a small example, but you can try and imagine how this would work with other systems that you would like to analyze in other scenarios with other fuels which could be threatened. A further example to show you the potential of this tool is a global design for performance-based design. So we are talking about the hedge combustion. Which would be our goals here? Ensuring integrity of the windows. We have one window which is closed here, so we have a glass receiving heat from the flames. The second window is left open, And then we have a third window with the PVC Persian blind down. So we could run a simulation to see what would happen. Actually, we obtained inspiration from the Odena fire from last year, when a house facade was almost burned down due to fuel accumulation. There was fuel very close to this north facade, and here we introduce a Douglas fir hedge, and we would now observe what would happen with these windows. So we want to ensure window integrity and also living conditions. So we are observing the potential of this methodology to verify the confinement degree offered by certain elements, sheltering. So objectives: glass shouldn't get to the crack point, 150. Persian blind shouldn't get to 140, and temperature should be under 60 degrees. And then we would need a 1.5 meter distance. In this case, temperature shouldn't be above 60 degrees, because this is needed for survival. Scenario: we would have two cases. The heat source is a Douglas fir hedge, but we would put it at two different distances. First, 2 meters, in a third case, 3 meters. And temperature would be 20 degrees, and then would be perpendicular wind to the facade. Here we see the evolution of the net heat flow, and red here indicates 80 or to 90 kilowatt per square meter, which is the emitting power of these flames. And then we run the simulation in the inside of the house. This is seen from the bottom. So we have this smoke layer entering the house through the window that was left open, and of course the smoke won't be that black, but this is just a simulation to know where this smoke layer is. So it would get through this window, which we left open. It would accumulate on the roof, it would descend, and then sensors would be at 1.5 meters high, and then we would start registering the values. So we can see how it's entering this room. We see open doors here, and we can see how it propagates. And then here we left a door open. Smoke is covering this room, and it propagates throughout the whole house. So if we analyze the virtual sensors, we can see the following. At 2 meters, temperatures and the Persian blind are above the threshold, but the 3 they don't. 2 meters, glass temperature is above threshold, but 3 meters is not. And here we have temperatures under 60 degrees. But when we speak about performance-based design, there are more restrictions. There's a restriction on visibility of the smoke, so that inhabitants of the house can live properly. But in a specific example, we would need to include all these additional parameters. So we can say that at the 2 meter distance, we have temperatures above in many rooms, except for 4 and 5. But with a 3 meter distance, we guarantee that temperatures are below 60 degrees. So the final result of this small example is that this system meets the performance requirements when the hedge is at 3 meter distance. So we see that the distance is a limiting variable. So these are just two small examples of a specific system which can be useful to inspire ourselves and to meet other cases, to meet the needs in other cases. And I've mentioned this in several other fora and with other colleagues. We can use this methodology to study the performance of radiant barriers. We know that non-flammable elements being used as fences rather, can be helpful, and we can see how efficient they are. We can also study the performance of other materials based on a similar system. We could classify the performance of one material or a different material. Then we can see the result of non-vegetal flammable material, and we can use the work that has been done in this fire engineering community, because their work has been tremendous, and they have studied a great deal of such elements. And as an example, you see here a graphic of heat fluxes for camper vans. And this takes me back to what Mario explained in Saint-Provence in last May with similar tests. And we've published some work on this issue, and we could use this data. And then there is the NATEC risk, that is to say, when natural risk interacts with technological risk. When we are talking about LPG deposits or other elements, we could analyze the effects of the flame on these deposits, and we could also evaluate the exposition of firefighting teams. Here I could include that the heat flux received at certain areas is not over 7 kilowatts per square meter, which would be the maximum for these areas. So these tools also allow us to draw these flux maps to know if we have values above the threshold, and to know if and then we can do such scenarios, and then we can evaluate shelters. Here, I would like to speak about the Australian example. They have already a performance-based code, that is to say, a methodology helping them to design shelters built specifically, and they do so with this with methodologies such as ours. So if we adopt this in the Mediterranean region, this solution of determining shelters so that residents can be confined there, we would need to check with this other methodology to make sure that these buildings and houses meet the living conditions. So, final remarks. I totally agree with the trans-scalar approach. Evaluation of vulnerability at microscale is very complex due to the interaction between buildings, fuels, and residents, and current regulation is not helpful at all. This problem has a huge degree of uniqueness, and then performance-based design can be of great help and bring about opportunities to ensure safety at microscale level. And then, well, based on this, we can start working to tackle some issues regarding design evaluation, recommendations, so that scientific evidence and the firefighting experience can be solidified in certain and scientific-based studies, and we can provide with new recommendations. So for me, the question is, how can we articulate all these options? How do we explore and exploit this methodology and these new technologies that can be extremely helpful to reduce vulnerability at microscale. So without further ado, thank you very much for your kind attention.